Okay, welcome to lecture 23. What we have been discussing from last lecture is the conjugate beam method for determination of deflection of statically determinate beams. Okay. Now, if you remember, this was the slide where we actually introduced the concept of conjugate beam. Let us before we go further, let us once again review this. The idea has been we have two problems. One is the problem of statics, one is the problem of kinematics. Problem of statics tells you that we have a structure subjected to some external load. Then the statics problem is determine the internal forces in the structure, and the equilibrium condition, equilibrium equation, static equilibrium equation plays is the premise of that process. Now, the kinematics is once we know the internal forces or once we know then use the relation between internal force and deflection or relation between stress and strain to determine the deflection or the deformation in a structure. Okay, and in this process the stress strain relation plays the important role. Okay, that is the cornerstone of this process. Now, conjugate beam method is essentially a problem of kinematics. In conjugate beam method, what we do is a problem of kinematics now formulated as problem of statics. And how it is done? It is done by exploiting the relation between the by exploiting the similarity between the relation similarity between the way the static variables are related to each other and kinematic variables are related to each other, and that similarity is shown in this slide. You see, the static variables are shear force, bending moment, and intensity loading Q, and kinematics variables are slope, deflection, and curvature. Okay. Now, what we discussed in the last class that curvature, the Q curvature is conjugate to Q, or then slope deflection is conjugate to M, or theta is conjugate to V. Or now, if we have a system, real system, where we need to find out the curvature, slope, and deflection. And then what we have to do is we have to construct a conjugate system where the intensity of the load is replaced by the curvature of this of the real system, means M by EI diagram of the real system. And if we do that, then shear force of this conjugate system will give us the slope of the real system, and the bending moment of the conjugate system will give us the deflection of the real system. So, this was the problem of kinematics originally we had. Now, instead of directly addressing them, instead of directly trying to solve the problem of kinematics, what we do is this kinematics problem is translated to a problem of statics, and then we solve this. So, the problem is reduced to determination of shear force and bending moment of the conjugate beam, and once we do that, the shear force and bending moment will give us the other kinematic variable of the real system. And this is the concept behind conjugate beam method. We demonstrated one small example where the uniformly simply supported beam subjected to uniformly distributed load. Now, so quickly, that was the problem we discussed in the last class. So, this is the real beam, this is the bending moment diagram of the real beam, and this is the conjugate beam where the loading on the conjugate beam is replaced by curvature, or in this case M by EI diagram of the real beam. Okay. Then in the last class also we said this is one part of the first step of forming a conjugate beam, but there are few other things that needs to be looked into while formulating a conjugate beam. Let us see what are the things that also important. Now, so one aspect is the loading on the conjugate beam. The loading on the conjugate beam will be the M by EI diagram of the real beam. Okay. Now, let's in order to appreciate the next part, next requirement for a conjugate beam, let us see one example. Suppose these are cantilever beam subjected to tip load. Okay. Now, what is the bending moment diagram for this bending moment diagram? This is the real beam, and what we need to determine? We need to determine, suppose, what is the slope at point B and what is the deflection at point B. We already know how to determine that using direct integration method and moment area method. Now, let us apply the conjugate beam method in this case. Whatever understanding of the conjugate beam method we have so far, let us apply that. So, this is the bending moment diagram of this beam. We know how to do this, and this is negative. You remember our sign convention is sagging is positive, but in this case this load will cause hogging in the beam. So, the bending moment is negative, and this expression is P into L minus x when x is measured from this. So, at x is equal to L, bending moment is 0, x is equal to 0, bending moment is PL. These distances, this bending moment is PL. So, this is the bending moment diagram, and then form the conjugate beam. Conjugate beam will be the, let us take the real beam, the same beam, and then replace the load by the curvature diagram of the real beam. Curvature diagram means the M by EI diagram of the real beam. So, M by EI diagram is this. So, since it is negative, the load will be upward direction in this case. So, what is the distribution load? Distribution of load is this divided by EI. Now, this is conjugate beam. Now, the problem is, instead of again determining directly the slope and deflection of this point, what we have to do is we have to determine what is the shear force and bending moment at B of the conjugate beam. So, this is now a problem of statics. We can apply the equilibrium condition, equilibrium equation, and draw the bending moment and shear force, or determine the bending moment shear force at a particular point. Let us do that. So, the theta B will be the bending slope shear force at B, and delta B will be the bending moment at B of conjugate beam. Now, if this beam deflects like this is the real beam deflects like this is the delta B and this is the theta B. Okay. What we know is that theta B will be the shear force of the conjugate beam at B. So, shear force of conjugate beam at B, which is VB, and we also know conjugate beam the method tells us that delta B will be the bending moment of conjugate beam at B. Okay. Now, let us visually inspect the beam. It is a cantilever beam subjected to a triangular load distribution, and the load is 0 here, and this linearly varies and maximum at the fixed end. Okay. By just looking at this diagram, we really do not have to do any calculation. By just looking at the diagram and applying our the engineering sense that we have developed, we can say that shear force at B will be 0. Okay. And we also can say that bending moment at B will be 0. Okay. Now, if shear force is 0, shear force at B is 0 and bending moment of B is 0, but just now we have seen that shear VB will give us theta B and MB will give us delta B. Does that mean that at this point slope and deflection is 0? Naturally not, because the beam deflects like this, slope and deflection they both are non-zero. Okay. Then what went wrong in this? Because we know that theta B and delta B are not 0 of real beam. Then what went wrong in this? Means since the results as of the concept of conjugate beam what we have seen so far, based on that and or same concept, same form if we apply, then we can see that no, that this is not applicable for this beam. So, it means this cannot be the conjugate beam of this. Okay. Now, why it cannot be the conjugate beam? Because one aspect of conjugate beam is the loading. That loading on the conjugate beam is M by EI diagram of the real beam, and another aspect of the conjugate beam is the support condition. Is it that whatever support we have in the real beam, is it the same support the conjugate beam also have, or the conjugate beam has different kinds of support? Okay. So, now next we will see that in order to form a conjugate beam, two steps are required. The first step is replace the load by MBI diagram, and the second step is the provide the support accordingly. Okay. It is not that the same support that we have in the real beam, the same support we need to apply for the conjugate beam. Okay. Now, so this next part is what is the role of support. Okay. Now role of support, let me explain this through this. Suppose these are different kinds of support. Okay. This is hinge support, roller support, fixed support, and this is without any support, means free end. This is an internal support, and this is an internal hinge. Okay. These are the different kinds of possible different kinds of support that we can have in a structure. Okay. Now, what this support says? This support says that since it is hinge support, deflection at that point is 0 and slope is non-zero, right. Now, deflection is related to shear force in conjugate beam, and deflection is related to bending moment in conjugate beam, and slope is related to shear force in conjugate beam, right. Now, since in this case the deflection is 0, means in the conjugate beam the bending moment at this end should be 0. Since at the real beam, real support, the slope is non-zero, then the conjugate beam shear force has to be non-zero. Now, you think a support condition where your bending moment is 0, but shear force is not 0. In the previous class, I showed you some bending moment diagram and asked you to, just looking at the bending moment diagram, try to understand the loading condition and the support condition. That exercise will help us now to do this. Now, what? So, we need a support condition where bending moment is 0, but shear force is not 0. Naturally, that support condition will be a hinge support, isn't it? Now similarly, now suppose this is a roller support, and what we have in the roller support? Roller support is this deflection in y direction is 0 here, and slope is non-zero. Okay. Now, deflection is related to moment, since deflection in y direction is 0. So, the support will be such that does not have any constraint against moment, and since the slope is non-zero here, so the support condition should be such that the support has non-zero shear. So, we need a support where shear is again non-zero, but moment is 0. So, this is a roller support. Since this is roller, this is a roller support. Now, let us see this beam. This is a fixed support. Now, this is a fixed support in a real beam, and what are the characteristic of fixed support? Characteristic of fixed support is all deflection and rotation all are 0. So, in this case, so theta is 0 and delta is 0. So, naturally, in a conjugate beam, since both are 0, deflection and slope, in a conjugate beam, moment and shear both have to be 0. Now, what are the supports that we have moment and shear is equal to 0? That is the free end. Okay, you remember a cantilever beam, which is cantilever beam, and the tip of the cantilever beam is free end. It is the tip of the cantilever beam. This is the free end. Okay. Now, so this is the, if this is the real support and this is the support in conjugate beam. Similarly, if the support is free end, suppose in this case this support is free. Okay. Now, if this support is free, what would be the support in conjugate beam? The free means it can have slope, it can have deflection both. So, both are non-zero. Similarly, in the conjugate beam support, shear force and bending moment both have to be non-zero, and both non-zero in where it is fixed. If the support is fixed support, then bending moment and shear force both are non-zero. Now, if it is a hinge support at intermediate location, what it tells you? It tells you that this has similarly. So, this this real beam support can be in the conjugate beam, this support becomes this. And similarly, if the real beam is an internal hinge, what is the internal hinge in the real beam? We cannot have in real hinge, we can have rotation at the real rotation is possible, but in this case now rotation is possible means what? Rotation correspond to the shear force. So, your beam will be such that the shear force is non-zero. So, these are the supports in the real beam and these are the corresponding support in the conjugate beam. Now, if some example, if this is a simply supported beam, is a real beam, and the conjugate beam also becomes simply supported, because real beam hinge support in the real beam, conjugate beam also it is hinge support, and roller support in a real beam, conjugate beam, just now we have seen the conjugate beam also it remains a roller support. So, if the beam is simply supported, real beam, in the conjugate beam will also be simply supported. And remember, the previous in the last class we first apply the conjugate beam theory, conjugate beam concept on a simply supported beam subjected to UDL, and we checked that the concept is working fine, because if the beam is simply supported, then the conjugate beam also it remains simply supported. But when we applied the same beam, apply the same concept for a cantilever beam, it did not work because of this reason. If it is a cantilever beam in the cantilever real beam, so the fixed support becomes free and this free support becomes fixed. Okay. So, if this is the real beam, conjugate beam will be of this, just the mirror image of this. But remember, in this example, what we did is, if this is fixed, that also we took fixed. If this is free, we took free here. So, though the loading is according to the conjugate beam concept, but the support condition was not. That's why the result did not come. So, if this is the real beam, then this becomes this is the conjugate beam. Okay. Now, so this is very important, because many places we make a mistake to identify what's supposed to be given in a conjugate beam. So, please be careful on that. Now, just quickly summarize the concept behind conjugate beam method. The next class will have some example on conjugate beam method. Now, probably this is the repetition, but since but let me repeat what is the concept behind conjugate beam method is. It is the problem where it is a process where the problem of kinematics is formulated as problem of statics, and how it is the real beam, instead of solving the real beam, we determine the internal forces in conjugate beam, and these internal forces are conjugate to the kinematics variable of the real beam. Shear force is conjugate to rotation and slope, and the moment is conjugate to deflection. Now, how to form a conjugate beam? There are two important steps for forming a conjugate beam. The first step is you take the beam, the length of the beam as it is, then draw the bending moment diagram of the beam, and then the MII by diagram will be the distributed force acting on the conjugate beam. The first step is in the conjugate beam is apply the load on the conjugate beam, and that load will be the M by EI curvature diagram of the real beam. This is the first step, and the second step is the support condition of the conjugate beam. You check the support condition of the real beam and check what are the kinematic constraint you have at those support condition, and based on that you decide what will be the support condition in the conjugate beam. Now, once this conjugate beam is formed, then rest of the process is just determination of internal forces in statically determinate beams. Okay. Now, what we do next class quickly apply this concept to some examples. Okay. And if you see any book, these concepts of conjugate beams probably is given in a very elaborative way. So, please go through that and make yourself comfortable with the concept. Okay. See you next class. Thank you.